Okay, so we're gonna do a clustering overview with a little bit of, kind of overview of unsupervised learning. So to start, what is unsupervised learning? And as usual, I'll be taking notes and I'll send out this doc later on as well. But what is unsupervised learning? I think the main thing you compare unsupervised learning to is supervised learning. And with supervised learning, it really depends. I like to think of it as what my training data looks like. With supervised learning, your training data is usually labeled or has some output that comes with it. So with supervised learning, you have a y variable, which is something you predict. Either, and the two that we've been dealing with, either classification or regression. And so you see when you feed things into supervised learning models, and supervised learning models will really just be like any of our classification models, our regressions. Some of you, I've introduced that we have other kinds of regression as well, like random forest has a regression, XGBoost has a regression. All of these you feed in an X and a Y. So you feed in features and you feed in like a prediction column. And based on, the actual values of your data, your model is trying to learn like relationships and parameters based on labeled data. So another way I like to put this is that the data is labeled. Unsupervised learning is unsupervised because there are no labels in unsupervised learning. So when you feed in data to any sort of unsupervised learning problem or model, you pretty much usually only feed in one X data frame. And unsupervised learning, you're trying to derive conclusions just from features. And the whole idea here is, there are two main kinds of unsupervised learning problems that we've talked about in this program. We have clustering, which is just like forming groups in your data. And you're not necessarily certain how these groups are going to look like, but just mathematically, what is the best way to separate your data into subsets? The other unsupervised learning technique that we talked about is dimensionality reduction, which is our PCA, which is, I'll get into that in a little bit as well. So that's a distinction between supervised and unsupervised learning. I think that's like a very good, I think it's a good thing to just be sure that you have an understanding of, like when you're using a model, is it supervised or is it unsupervised? Comes up a fair amount in job interviews as well. Questions about that? Cool. So let's first talk about clustering. And before we dive into like details of clustering and like applications and all of that, we'll go into the types of clustering. So two main big categories of clustering. We have hard versus soft clustering. Hard versus soft clustering. So hard clustering, every data point gets a label of a cluster. And then with soft clustering, each data point can belong to multiple clusters with different probabilities. So I think I'll type in that later. And the whole idea of clustering is to just form groups. Forming groups based on the distribution of your numerical data. Distribution of your numerical data. So sometimes, and if you end up doing, your post-clustering EDA, you might see results that you don't expect, right? So let's say you are trying to cluster, I always come up with this example, but you're trying to cluster sports people, like football players, for example, and maybe you expected, okay, they're going to be clustered based on, I don't know, whether they're an offensive or defensive player. But based on your clustering results, you might get a different kind of grouping, right? Because it really depends on mathematically, what are the best groups. So you might guess that, let's say you do two clusters, you might guess, all right, maybe it's going to be offensive versus defensive. It might be that your actual results show maybe it's like tall players, short players. So That's why it's important to do post-clustering EDA, which I will get into later as well. So that's hard versus soft clustering, and that's an overview of what clustering is. I'll come back to dimensionality reduction at the end because I don't want to like go into different topics. But all right, hard versus soft clustering. Hard clustering are the ones that we talked about at the very start of mod 4. The two methods that we are aware of with hard clustering are k-means clustering and hierarchical agglomerative clustering. So for our hard clustering, we have k-means and HAC. They work slightly differently. If you want to, I'm not going to go into details as to how exactly they work, but k-means works basically by choosing random points to be centroids and then forming clusters based on which points are closest to which centroids and then readjusting. If you remember back to like when we talked about clustering first, there was this GIF of like, you know, starting points and then these centers just keep shifting. That is k-means clustering. HAC is the one with the dendrogram. HAC is the one that every data point starts off as its own cluster. And then based on which data points are closest to each other, they just merge and then form bigger and bigger groups until you get to the number of clusters that you want. Something to note is that for all of the clustering methods, hard and soft, that we're going to talk about today, you have to define how many clusters you want. And I'll talk about how to define that in a little bit as well. So with hard clustering, we have k-means and HAC. And basically with hard clustering, each data point is assigned to one cluster. With soft clustering, the only thing that we've touched on is LDA. So LDA, which is latent Dirichlet allocation, is specifically for text data. And that's what I talked about when we talked about NLP. So LDA is a soft clustering method. That does not mean that you cannot do hard clustering with text data. You actually can as well. But soft clustering basically means that each data point can be assigned to multiple clusters with different probabilities. Questions about this at this point?
Yeah,
Right.
I actually have a quick question. So, but if we do use, you know, like clustering to reduce dimensionality with NLP, that would mean we're losing some, like at some level, we're losing information that would increase the accuracy of the model, correct?
That's right. That's correct. So clustering is not the same as dimensionality reduction, but in both cases, if you're clustering your data and you're just using like cluster labels as your new data, you do lose information because you're doing some sort of aggregation. You're doing some sort of, you know, summarizing of your data with simpler data. So you do lose information. Same with dimensionality reduction, you know, like when we were talking about PCA, there was that, if y'all remember PCA, which I know it's been a while, when you lower your dimensionality, PCA, and I will get back to that and go over all of this again, but with PCA, you're trying to maintain as much variance in your data as you can with as few dimensions as needed. So yeah, as you lose variance, you basically lose the variance in your data. You literally lose how much your data varies because it's representing like 100 dimensions into 10 dimensions. You just don't have room to vary your data as much. So yeah, all of these do cause you to lose some information. Sometimes you just have to, like if you find that like models are taking very long to run and it's not feasible to run like your models for hours at a time, dimensionality reduction is something that I would recommend. But yeah, it is understood that you do lose information with basically less columns, less information.
All right, sounds good.
Anything else? All right, well, at any point, as usual, feel free to interrupt. Okay, so we've talked about types of clustering. Now let's talk more about applications of clustering, and in the applications of clustering, different things that you should consider. So one thing to consider, let me do this, number of clusters. I think this is something that really depends on what it is that you're clustering, the number of clusters that you should go with. In the example of like clustering sports players, it really depends, right? Like sometimes maybe you're, I don't know, the coach is like, I want specifically 3 groups of players, then you have no choice but to cluster your players into 3 groups. Or if you already know like the number of clusters that you want to have, you have no choice but to stick to that number. And if whether you use k-means or HAC, the model is going to look for the mathematically best way to group all of your data points into the number of clusters that you want. So might be, what's the word, constrained by your business problem. So you have no choice but to stick with a certain number of clusters. So that's,
here's one quick question. So now let's say now I'm working on an NLP, and like I want to shortlist few categories. Just let's say 2 or 3 categories. Since I'm working on the COVID data, right? So if I want to shortlist people, for those people who have been vaccinated as one cluster, those people who haven't been vaccinated as the another. So when I create these clusters, so it's based on only on those columns.
That's actually a really good thing that you brought up. So if you are trying to, there's a difference between clustering and subsetting. So clustering is going to divide your data based on whatever columns you're telling it to divide upon. And so let's say, I don't know, if you're using tweets, the way clustering works, it might not cluster your tweets in like vaccinated, not vaccinated. That's just, it might not be that way, because through clustering, the clustering algorithm might find that there are other better, mathematically better ways to split up your data. What sounds like will be more appropriate in that case would be just subsetting. Is there a way that you can figure out subsetting like through other methods of like, all right, based on certain words used, these people were vaccinated, these people were not, because the distinction between the 2 groups might not be spatially mathematically drawn. If that makes sense.
So if I just, let's say if I've already distributed it into the words, the maximum number of words used, and I want to cluster between 2 highest number of words used. It might be like, okay, some with this what I say, let's say good and bad, right? So the number of times good has been used is highest, and number of times the vaccine is bad has been used the second. So if I want to just cluster them, or I just divide those data and do some other model, or clustering works the best in this.
Yeah, so if you want to cluster text data based on content, and if you really want to restrict, all right, what word uses, what words do I want to consider? You can definitely subset it that way. So let's say like you take your top 10 most commonly used words and their word counts, you can cluster that data. But the thing that I want to highlight is it might not give you the results that you expect, right? Because let's say you have the word good and bad. You don't know if like for sure the good and bad are referring to like the vaccines, or is it referring to like, oh, the vaccine wasn't that bad, you know? So you have to be aware that like, this is a mathematical algorithm. It doesn't have much understanding of your text. Which actually I can segue by, not a segue, but a situation in which that information could be taken into account is if you use word embeddings. If you cluster word embeddings, some meaning is taken into context. So that could be something that you explore as well. Yeah.
So now what I understand is like if let's say the tweets are already divided into 2 segments.
Okay.
Post that, this will be helpful, I guess.
Say the last sentence again.
So after I divide this, let's say in the NLP project, which was earlier, it was already mentioned that which is good and which is bad.
Got it. So it's already labeled.
Already labeled. So this probably might help. Like once the labeling is done, after that, this might help, I guess.
Okay. So if you want to find out what people are talking about within like the vaccinated group and the non-vaccinated group, I'm going to talk about that in a little bit. Am I? No, I talked about this last time, but that could be something that you use LDA for.
Okay.
So let's say you already have your data set for these people are vaccinated, these people are not vaccinated, to see what they're talking about and to like derive some information from the bulk of text, I would use LDA.
Okay.
Cool. All right. So yes, number of clusters. Back to number of clusters. If you are not constrained by the number of clusters in your business problem, you basically get to choose how many clusters you want to go with. And sometimes it's very, very hard to decide because yes, we have the metrics that we talked about. So there are some metrics for determining best number of clusters. And these are your elbow curve, your silhouette score. How do you spell silhouette? Silhouette, yeah, silhouette score. And there are a couple others that are highlighted in the labs. You can use these to determine, all right, what's my best number of clusters? But something that to be very aware of is you have a lot of flexibility here. But you can be flexible. So let's just say your metrics tell you that for clustering sports players, a good number of clusters is 3 clusters or 8 clusters. And they both those numbers are giving you like the best metrics. You actually have a lot of freedom as a data scientist to choose what to go with. Because it's an unsupervised problem, you have to take into context like, all right, in this situation of clustering my sports players, is it better that I give the coach 3 groups of players or 8 groups of players? So you really have flexibility in deciding the number of clusters that you want. So just know that like, you know, the metrics are not the end all be all. The metrics is just a tool that you can use to help you decide the number of clusters. Any thoughts or questions about that? I think that's something that trips a lot of people up because they're like, oh wait, this silhouette score is telling me that I should go with 5 clusters, but 7 just makes more sense. So that's something that you
a couple questions. First of all, which labs do we talk about those in again? So I can take a look.
Oh, that's a good question. Okay, let me take a look. So we're going to go to your homeroom. I put it in, it's in phase 4. It's probably going to be, let's see, probably one of the ones in here. One of the ones in 34. Yeah. I don't know which one it is. Probably.
And then how do you decide like if it's the best? Like do you run train test splits at all, or like what do you decide?
Yeah, that's one big pro and con about unsupervised learning is that there's no way to verify, right? Like with supervised learning, because the data is already labeled, you can say, all right, I can validate my model by saying, right, okay, it matches the predicted and the actual labels match up. So you have some evaluation metric. That's not the case in clustering. In clustering, I think it really depends on the kind of data you're dealing with, like how much information can you actually glean from the data. Yeah, there's just no way to, you can use like these scores to help you determine like, are these good clusters, but also note that the scores are going to be very relative to each other. So if you just like say, all right, let's do 3 clusters, I get a silhouette score of, I don't even know what the scale is. Let's say silhouette score of 5. This number 5 is not going to mean anything until you compare it to like the silhouette scores of other number of clusters. So 3 clusters give you a silhouette score of 5. Maybe 4 clusters will give you a silhouette score of like 6, and then it's all relative to each other. So yeah, doing clustering does require a lot of tuning. I will say it also depends on which algorithm you're using. Something that I forgot to mention earlier is that for k-means, each time you rerun the clustering algorithm, you can end up with different clusters, which is, you could use like a random state to help with that, but that's just the nature of k-means. Each time you rerun, you might get different clusters, different results. And for HAC is not the case. HAC is the same every time you run it. So yeah, that's what makes things a little complicated. I would say if you care more about similarity of your points within a cluster, HAC is the way to go. But if you care more about overall groups, k-means is more of the way to go. I know these are very like vague descriptions, but that's how it is. It really also depends on the variability of your own data set. You might get very similar or very different clusters when you use these 2 algorithms and like compare results. So that's something to also think about. I don't remember if you had any other questions that I have not addressed yet, Harry. All right, that's number of clusters. I think the main thing that I want you all to take away from this section is that your number of clusters you can be very flexible with the number of clusters that you end up choosing. It just really depends on what makes sense in your project. Like in one of my last cohorts projects, someone was like, the best number of clusters seems to be 40, but 40 does not make sense in this context. So therefore we just rolled it back to, I think, like 10 or something like that. So it's very, very context dependent. Cool. Something else, which is a big thing I want to talk about clustering, and I think will be relevant to a lot of you, is clustering text. So I talked about LDA. LDA is a topic modeling method. Topic modeling from GenSim. The package that you use is GenSim. Soft clustering method, it will basically tell you what are the main things people are talking about. Will help you answer what are the main things, or what are the main topics this data set of text is talking about. That's what LDA is for. Because it's soft clustering, and also there's that really neat visualization that you can really easily inspect each cluster and see what the main topics are. So LDA is a really good one for text data. If you want to be a little bit more strict with the clustering, one very, very common use case of hard clustering methods in text data is in generating labels, which actually also can be done with LDA. For example, if in LDA, out of the model, you can actually extract for this document, it is 50% topic 1, 25% topic 2, 25% topic 3. That is actually something that you can get out of LDA. But if you want to generate like hard labels, let's say you have, I don't know, a bunch of news articles and you want to do classification, but you don't have labels to make classification on, you can actually create labels through clustering. So creating labels through hard clustering methods. So how you would do that is first cluster your text, and then through that you can maybe also use that flexibility of deciding how many clusters you want. So first, let's move that back, cluster your text data. And after you cluster your text data, do some post-clustering EDA. Essentially to label your cluster. Does anyone have any questions about these 2 steps first?
Yeah. Just one thing. When is the best time to use clustering for text?
Honestly, two main times. if you already have like labeled data, or if you want to do like an analysis, LDA. And this would be like, I would say probably after or within your EDA phase, just to understand what your text data encompasses, like what are the topics that your data is talking about. That would be a really, really good use case of soft clustering. Another good point would be if you are at a point where you would like to employ machine learning methods in like classifying your text, then this method would be right. So after you do like your regular NLP EDA, if you next want to build some sort of classification model based off of what your text is talking about, or like based off the subsets of text, you can do a clustering to basically generate your Y column that doesn't already exist. Does that make sense? I feel like that was not a coherent English sentence, but hopefully that makes sense.
But that, I mean, I could understand.
Okay, awesome. So yeah, let's just say like you have a bunch of news articles that you just forgot to scrape their topic for. You can then throw all of the text of your news articles into a clustering algorithm, maybe come up with like, for an example, 3 topics. So let's say you have like, I don't know, business articles, entertainment articles, and then you have, I don't know, politics articles. So let's just say you have these 3 topics. It's important to note that the clustering labels are not always going to match up with what they actually are. I think that's why, especially these days still, manually labeling data is still a job that exists. But at least with these model generated labels, you can then build some sort of classification model using these generated labels.
Wait, so suppose like you do that news, you have 3 topics, what you like, politics, sports, and business, and you run the clustering models, but it comes up when you, maybe it does it geographically. Oh, it has Asia, Americas, and Europe. Like it clusters them differently than you thought it would. Could that happen?
Yes, absolutely. So that's why when you're going into clustering, it's best not to have like a preconceived like idea of what your clusters will be. It's really like through the post-clustering EDA, this is where you're like, okay, after I've done my clustering, it looks like everything in cluster 1 is like, okay, maybe they're just talking about like Asian news. And then cluster 2 is European, and cluster 3 is American. So yeah, labeling comes after the clustering is actually done.
You do, that's what you EDA afterwards, and that's how you figure out what each, maybe you'd run a word cloud or whatever it is, and figure out what all is. Okay.
That's right. Yeah, that's a super important point to just hammer down, is that I think also something that I mentioned at the start of this is clustering doesn't always go the way that you want it to. I think in most cases it does not. Not to backtrack, but I think it's also important to mention, and where should I put this? When you're clustering your data, because a lot of it is doing it like through distance and through like similarity, it's very important to scale your data before you cluster. So let me see where I can put this. Don't forget to scale your data before you cluster. And scaling your data essentially just make sure that every feature, every column is considered fairly evenly. Each column / feature is considered evenly. That's something I forgot to mention earlier. If you're doing text data, and if you're using like, if you're using TF-IDF or count vectorizer, you don't really have to scale those because the scale of every feature is going to be about the same. But yeah. Okay. So what was I talking about? Creating labels through hard clustering methods. From your clustering algorithm, so your clustering model .predict will basically clustering.predict will basically give you an array of predicted clusters, which you can then use as your Y column for classification. So that's another really good use case of clustering. if you don't have labeled data and you want to employ some machine learning to garner information, because after you get these labels, and let's say you build a random forest model to just reclassify everything, one, you can figure out where your clustering model went wrong, and maybe you want to adjust the cluster labels for some data points for anything that was misclassified. Another thing that you can do is through feature importances, you can actually find out a lot about clusters as well. Through feature importances, you can find out what are the words or what are the features that are leading to a point being assigned to a certain cluster. Questions about that?
So will lasso work here?
Lasso. So lasso is a regression model, and regression clustering results are usually for classification. So lasso is for predicting something continuous, like a continuous unbounded value, like, I don't know, I'm guessing something like number of COVID cases. That would be something that comes out of clustering. Sorry, that comes out of lasso. Clustering will get
based on the I was just thinking when thought came in, like if for the location specific place where if I do feature importance, will lasso work there? That's what my thought was, but I think that may not work because it's basically to classify. Okay.
Yeah, all good. Yeah, I think lasso is for predicting continuous, just because it's a regression model, so wouldn't really work here. But I mean, you can also be creative with your clusters, right? Like if your clusters, you can also get probabilities of clusters through, I think not through HAC, but through k-means. You can actually get the probability of a point belonging in each cluster. So k-means can actually kind of do soft clustering as well. And maybe if your clusters end up being something that's ordinal, so let's say your clusters end up being like, instead of COVID cases, maybe it's low, medium, and high number of COVID cases, that could feed into a lasso model. But whether it ends up clustering that way, that will be a huge restriction to your ability to do that. Cool. Those are the main points that I wanted to talk about regarding clustering. I think LDA I talked about a lot more in more detail during the NLP session. So main takeaways from clustering is that it can be used as a really good EDA tool to just get a sense of how your data is spread out in space, in numerical space. And yeah, it can also be very helpful in generating labels for your data. And also that you have a lot of flexibility because it's an unsupervised learning problem. You have a lot of flexibility. Like if you see that, let's say you do 5 clusters, but 2 of the clusters are smaller and kind of close to each other, you can pretty much merge those clusters and make them into one. That's also something that you can do. So there's a lot of flexibility when it comes to clustering because of its unsupervised nature. All right. Before going back to dimensionality reduction, any questions regarding clustering? All right, I think with like the knowledge that we have now, after going through a lot of mod 4, because I know we talked about clustering at the start of mod 4, hopefully clustering makes a little bit more sense, and maybe you have ideas of how you can incorporate it into your project. Not necessarily, you don't have to, but it's something that's just good to be aware of. All right, so dimensionality reduction. The main one that we had talked about is PCA, and here you can actually see it was the first topic in mod 4, phase 4. So PCA is there. I will say PCA, the algorithm itself, is actually done with linear algebra math, and is one of the more complicated math algorithms that it's used in our curriculum. So I would say, in terms of understanding how PCA works, I don't think you would have to explain too much of like how exactly the algorithm works. I think at the most, you might say that it uses SVD, which I know is confusing because our recommendation algorithm is also called SVD. But I can talk about that more towards the end as I talk about preparing for interviews, but just so you all are aware. So there are actually many different kinds of dimensionality reduction algorithms. PCA is probably the most common one because it helps to maintain variance. So PCA is just one of many algorithms that reduce dimensionality. And the main goal of PCA is to reduce the number of columns while maintaining variance in data. So what this means is that, let's say you have 100 columns, but maybe 2 of the columns have like almost all the same value. This is a very, very simplified version of explaining PCA, but if 2 of the columns have like almost the same value for every single row, you essentially those columns will not be as important for your data, right? If let's say you are collecting data on like, I don't know, the weather of every single day across an entire year, and let's say in some area there was just no rain the entire year, rainfall in that data set will just not be very important because there's no variance in the rainfall. So if you were to do PCA on that data set, the rainfall component will be very close to 0. That makes sense. So the whole idea is maintaining as much of the variability in your data set as you can with as few columns as you need. Another thing that's important to note is that the result of PCA, the columns that result after you run a PCA algorithm, outputs principal, it's called, each column is then called a principal component. A principal component. Principal, is it principal with an AL or LE? I always forget. Outputs principal components. Hopefully, I think it's that one. Let me just double check real quick. Principal components. AL, okay, great. So it outputs principal components, and each PC is a linear combination of every other feature. And I'll talk about that in just a sec. Is a linear combination of every original feature. So what that means is, let's say you have 10 features. Say you start with 10 features and lower it to 2 dimensions. PC1 and PC2 will be your result. PC1 will be basically like, as an example, 0.1 times feature 1 plus 0.2 times feature 2. Plus, it can also be negative actually. Maybe it's like 3 times feature 3. So on and so forth. So that's what it means by linear combination. Questions about that? And I don't know, 8 times feature 10.
Will it be 0.3 or just 3?
It doesn't matter. It doesn't matter. It can be any number.
Okay.
Yeah. And so what you'll see is that for that example where I said like rainfall was a low variance feature, rainfall will actually have a coefficient very, very close to 0. Yeah. All right. So and then PC2 will be same as PC1, but with different coefficients. So that's what PCA is. And actually, when you do PCA, you can actually extract these components. And through these components, you can actually sort of derive or infer what are the features that are more important to this data set. What are the features that have more variance and what are the features that don't? So that's something that you can study. So features with low coefficients are usually less important or have less variance. Cool. Questions about PCA? All right, well, what about when do you want to reduce dimensionality, right? So reasons why you would want to reduce dimensionality is one, if you just have too many columns. So for algorithmic efficiency. Because fewer columns you have, a lot of your algorithms and models will just run faster because there's fewer columns to look at. Another main reason that you could use PCA for is for visualizations. If you have like a 10-dimensional data set and you want to like see the distribution of your data points, you cannot plot in 10 dimensions because we cannot see past 3 dimensions. So doing PCA and lowering it down to 2D or 3D, you can then visualize the distribution of your data. Turning data into 2D or 3D so that you can visualize. However, or actually let me do downsides here. Oops. A main downside of PCA is you lose interpretability. You lose interpretability. Because let's say you do PCA, and then let's say you have your data set from 100 columns down to 10 columns, you put it through a random forest and you get your feature importances. The feature importances are going to be the importance of your principal components. And how useful is it to have, it's basically another layer of decoding you would have to do, because your feature importances graph will show you, all right, PC1 has an importance of what, but PC1 is made up of a combination of all your other features anyways. So, I mean, you could technically break that down and say, all right, since PC1 is mostly feature 5, for example, you could say that feature 5 is very important, but sometimes it's not always as straightforward as that. So one big downside is you lose interpretability when you do any sort of dimensionality reduction. Questions about this?
Yeah, I have one. So when you're doing like count vectorization or TF-IDF, you end up with a lot of columns. You end up with, each word is its own column. So do people use PCA in NLP?
Yeah, you can definitely do PCA with NLP, especially because NLP you usually end up with like number of columns being in like the thousands just because of like unique words. Yes, you can use PCA with NLP again, but you just lose the interpretability. Like, right, when you want to figure out what are the most important words that lead to classification one way or another, it's a lot harder to do that once you've done PCA. So usually if you're dealing with words, I usually recommend that you lower your features in another way. And actually, let me put that here. Let's see, PCA on text. When you're doing PCA on text, you lose interpretability using PCA. Therefore, I recommend lowering dimensionality using some of the vectorizer's parameters. And I'll explain, I'll go back and I'll pull up documentation in a little bit. Dimensionality through the vectorizer's parameters. For example, max df. I think there's another one called min df or something like that. So let me pull it up real quick so we can have some context. Oh yeah, max features. So I do recommend that if you want to lower dimensionality, or if you do your count vectorizer with the default arguments and it's just too much for your model or too much for your computer or notebook, you can definitely reduce it through here. So using some of these features, and I did talk about this when we talked about NLP last week, but let's say doing count vectorizer gives you 10,000 columns. That's just too much for your computer to handle. You can use the max features here and just consider like the top maybe 500 words. And that can be like a much more, I think it would be a much more efficient way of dealing with high dimensionality. just because by doing it this way, your computer is never saving that 10,000 column data frame. And that's usually what breaks your kernel or like makes you run out of memory. So by adjusting these parameters, you skip that whole step of having a huge data frame that you have to whittle down. This will just output straight up like the smaller, relatively smaller data frame. So if it's text data, I do recommend luring it this way first, because what are the chances that like the 5,000th most common word is going to be very important? So that would be my recommendation. But of course, yes, doing this, you also lose information. But I think here it's a more efficient way of dealing with it, especially with text data, because we have these built-in vectorizers. And by the way, same for TF-IDF as well. So let me just copy and paste this for easy. And actually I want to mention max features as well. All right, PCA on text. All right, I have like mild OCD, so I need to do this. All right. What else did I want to mention? Okay. Any more questions on like clustering or reducing dimensionality on text? So I want to talk about another dimensionality reduction algorithm that might come in handy. Okay, so I think I've mentioned this here and there. I honestly forget, but there's this other dimensionality reduction technique called TSNE or TSNE. I forget what it's called off the top of my head, but let me actually look up. Here. So TSNE actually works, and the code is exactly the same as PCA's code. It's just you're instantiating a different thing. Stands for T-distributed stochastic neighbor embedding. And what it does is, instead of maximizing variance like PCA does, TSNE actually maximizes, I think, in some way, separability of your data. So I know it's kind of similar, but TSNE tends to work better if you know you want to visualize. So I do recommend, and let me actually bullet point this here, better for visualizing. If you know you want to reduce the dimensionality of your data, you can actually try using PCA and try using TSNE just to see which one gives you better results. It's very hard to say without context of your data which one will give you better reduced dimensionality results. So, but TSNE is usually better for visualizing. So let's say you have, let's say you want to visualize like your 10 class data set in space. If you use TSNE, your 10 different colored points in your scatter plot will be more separated. So yeah, just wanted to mention, if you want clearer visualizations of like high dimensional data, TSNE might be a little bit better. Something to try out. Cool. I think that is most of the unsupervised learning that we talked about in all of our curriculum. Any questions? I know this is a lot of information and a lot of this stuff we haven't seen in a while. But I do think like if you find yourself looking for things to add to your project, unsupervised learning could be something worthwhile. Any questions?
I have a question about the projects.
Yeah.
So we were slacking about doing a train test split. When you're running the models, I'm doing NLP as like many of the people are. So do you vectorize it before the train test split or vectorize after the train test split?
That's a really, really good question. And I actually want to put it in our NLP. I want to put it in our NLP document. So let's see. Yeah. When do you train test split in relation to vectorizing? By default, you should train test split before, but I also want to talk about the implications of doing train test split in different places. So by default, before vectorizing, you do train test split. So the idea of doing chain test split before some process is to prevent data leakage. If you think about, because it's actually different for count vectorizer and TF-IDF. If you think about how the numbers are, how you get the numbers for count vectorization and TF-IDF vectorization, count vectorizer really just counts the number of times a word appears, and that's your number. And so whether you do chain test split before or after count vectorizer actually doesn't matter, right? Because the values in a single row are not affected by values in other rows. So technically, if you do your chain test split after count vectorizer, your values won't change. However, in TF-IDF, because it's inverse document frequency, you are reweighting your values based on values in other rows. You have to do your chain test split before, because you don't want to consider the text status in your test set. So that's why it's a little bit tricky. I'm glad that you brought it up as well. I also forgot to talk about it last time. So by default, you should chain test split the sooner the better. Actually, some people have, and I don't think it matters so much, but there are actually like some data scientists that will even do their EDA on only a train set, just so that your test set is truly unseen data. I feel like EDA doesn't really affect your model that much because you're not using results from EDA directly in your model. So therefore, I don't make that case. But yeah, usually to just prevent data leakage and to have like a true holdout test set that your model has zero information from, you want to do your chain test split earlier in the process. So it's actually kind of similar to like scaling actually, because if you think about how TF-IDF works, TF-IDF reweights based on, you know, other rows. And so same as scaling with like min-max scalar, right? Your min and max will change based on how many rows or what rows you're considering. So yeah.
And also with the Y column, so you know I'm doing classification. I have 5 categories. So when I feed in the you know, I lematize it all and I have a data frame of just lematized and tokenized words. What do I do to get in the Y column would be, I guess, you know, all the categories. Do I remerge the Y column to that data frame, or how do I do the target?
Mm-hmm. You don't have to put it back together, but you are going to use them together because you start off with just like your one column, one long string data. And when you plug it into the vectorizer, the order of your rows stays the same, right? So like row 1, 2, 3, 4, 5 in its long string form will just be translated into like many columns of the same data.
Right.
If you're using Scikit models, and I think, yeah, probably will be using all the Scikit models, it takes .fit x comma y, so you don't have to put it together.
Okay.
That makes sense? Yeah, so you don't have to put it together. You could, if you just want your data to be in the same data frame, you can. Maybe you want to do that for like a little bit of EDA, so you can filter, okay, these are the 0, 1, 2, 3, 4 classes. But yeah, you don't have to put them together for the modeling.
Okay.
Yeah, because there's always, even when we were doing like numerical data, there was always that step of like X equals to data frame drop the Y column, right? Drop target. So those always end up being separate before the model, as you plug them into the model. Cool. Anything else?
Yes, one question. So when I was like pulling in some data, it came in as XML files. So
Okay.
does PD? Yeah, I mean, pandas have the facility to read XML files, like pd.xml, or like we read CSV.
Yeah, good question. I actually don't know. Pandas. So XML structurally is very similar to a JSON file. I don't know if they have it built in, to be honest, but let's see. Off the top of my head, I think that you should be able, yeah, look, see, here they basically create something that parses it for you. So therefore, Yeah, it looks like you would have to go through additional steps, but the data is there. And because it's structurally very similar to JSON, which is what we have worked with, I imagine there are ways to get there, just not directly through pandas, unfortunately.
So some of the medical sites which I was trying to get into, and they just, I mean, without APIs, they just say that, okay, you register, and if you're a part of a medical group, then we can send you an XML file and you send it across. But then, like when they send the XML files, I just want to know whether it needs to be converted into JSON and then, right?
Yeah.
Because they use in the entire medical fraternity, they use XML as one of the main ways to, I mean, transfer them any kind of data.
Yeah, I can imagine, because it's XML is memory wise more efficient. I don't know if it's more efficient than a dictionary, but XML was the predecessor of JSON dictionaries. So I know it is more efficient to store data versus in the CSV.
Some of them
So,
said
yeah.
that it's more secure, so I don't know how it is. Like
I don't know anything about security on my end, but yeah, there's definitely a way. Like Python can definitely read XML. Pandas is where I don't think so. So you just have to like use other libraries to convert it from XML, probably to a dictionary first, or like a JSON first, and then you can probably plug it into pandas.
Oh.
Cool. Any
one more question. Anything you know about the IBM Watson API?
Not.
No?
I've never used IBM Watson, but I do have a few of my like students who went to work at IBM, and I can always, I don't know if they work with Watson actually. So I've never used it myself, but if you want to use it and you're running into issues, let me know. I can.
I was suggested, but I have not even touched based on that. I mean, getting into research of that.
Okay. Yeah, I don't even know if it's like I don't think it's a free product. I don't,
because when suggestion comes in, it does not come as free.
yeah, I didn't think that IBM Watson would be free. It's very, very powerful.
Yeah.
And like for like machine learning and just as an AI platform. So I don't imagine it's free.
Yeah. Okay. Let's see.
Well, all right then. I will see you all at your one-on-ones. Excited to see your MVP presentations on Monday. We're hopefully gonna.
One last question. Where's the repo for all the Google Docs that you're typing up there?
So I've actually been putting them. I've been linking them on the homeroom. Sorry. Yeah, this is your homeroom. So once I'm gonna like make sure all of what I was typing today is accurate, and then I will link it onto here. So this is the NLP doc.
Okay.
These are the Capstone guidelines. Actually, if you scroll down here, I have all our past project guidelines, which actually like I go through like a more in-depth process of doing like NLP classification in the mod 4 project guidelines. So you can actually see like a breakdown of what that's supposed to look like. I also have, and these I will actually talk about later, but these are more like interview questions, warm-up questions, post-graduation resources.
Okay.
These are here.
Yeah.
If you want easy access to here, it's actually in the Slack. It's on our Slack. I don't know if you all have seen. Yeah, it's linked at the top of our Slack.
So the one with the learn is going to end 4th night or 5th night?
I'm not sure exactly. I would just say if you have anything important.
4th night.
There, yeah. Just assume you lose access at the earlier date. So yeah, you're gonna lose access to your learn co-curriculum this coming Monday. I don't know if it's the night before or like day of, but yeah.
But everything that's on is on a new portal too, so it doesn't really matter.
Yeah, it's just that, yeah, exactly. So it's not like you have any work saved on Learn, because Learn doesn't save your work anyways. And also like after you all graduate, you'll actually get instructions on how to download all of the curriculum. So for example, if you didn't end up cloning a bunch of labs, there'll be options to download everything as well.
Well, I saw in here you have like options in Canvas where you say it says like download the curriculum, kind of something like that.
Yeah, I think I mean, I don't need to download it on my end, so I've not done it, but like my students who just graduated managed to download every single like reading and lab, and also all of their like projects. But I don't know why, because for cohorts that have been on Canvas, my project feedback is actually all in this system as well. So actually, the last week of Capstone, right before you all submit, I'm going to walk through a submission process on Canvas, which is slightly different from Learn, but I think is a much more streamlined. It's a much more streamlined process. You don't have to like submit every little thing.
The blog thing got solved. I mean, those people who have put blog on Learn.
Oh yeah, so people who blogged on Learn, the blogs. It's weird because your blogs will still be there. You just won't have access to changing them. So I do recommend that if your blogs are on Learn, copy them over and publish them on Medium or something.
Okay.
All right. Well, I look forward to your MVP presentations on Monday. We have some other students who don't usually come to study group that have told me that they're going to do their MVP presentations as well. So that'll be exciting to see. But yeah, other than that, my next week is also looking pretty open. So if you want to book additional one-on-ones, feel free to. All right, I will talk to you all soon. Have a good almost weekend, everybody. Bye.
Bye-bye.